Alright. Now this one stands out as its own because this cycle is meant for rotary turbine, that means rotary engine. Whereas all these are describing your reciprocating. Okay. Now this cycle will be very simple. So I remember, okay, basically, right, the theory is the same, right? This one, right, will apply to all. Let's take life very easy. And this one, as we have seen, right, comes from our Carnot cycle. Correct or not? The reason why we cover Carnot cycle is to understand the fundamentals. Alright, so you notice that in the case of a Carnot cycle, right, the cycle is very simple. Two isothermal process, two isentropic process. But in the actual cycle that we are encountering, practical cycle, they are more complex than that. But basically, they still involve these four quantities. Alright, so now when it comes to Joule-Brayton cycle, same thing. So now I've given out the notes. So now we look at it. Okay, here. Okay, this is the plant layout of the Joule-Brayton cycle. It's just like our work combustion cycle and so on. This is our plant layout, right? It works from there. So now our Joule-Brayton cycle consists of all these components. Okay, alright. So let's consider, right? So look at it. The list now. It involves compression work, heat supply Q1, expansion work, heat rejected Q2. Right? So this one is easy to deduce, right? You know why? Because you have positive work, negative work, correct? Positive heat, negative heat, that's all. So it involves heat and work. It's very simple to recall. Correct? Compression work, expansion work. Heat supply, heat rejected. Okay? So these four quantities, let's see how it appears in our Joule-Brayton cycle. Can you see the first one? Compressor work. So in other words, your gas will come in, right? The gas comes in, then this is a compressor, it will compress the gas to a higher pressure. So gas will come in, compress to a higher pressure. So the gas at higher pressure will be heated up. Can you see now? So heat added. Correct or heat added in the next one. So you adding heat. So when it comes up at point 3, right, you will expect very high pressure gas and very hot gases. Okay, so you can be sure now the gases at that state will contain very high enthalpy, correct, internal energy content. So if you allow this gas to expand, right, expansion work, right, our next one, where is the expansion work? So you will expand in the turbine, something like this. So it will be, in the turbine there will be rotor plate and so on. It will rotate our turbine. So this is where now you will get out the work. You follow now, the work will come out from there. Okay, so now when the gases comes out of the turbine, it loses, not loses, like give out a lot of its internal energy or enthalpy, energy content. Right? So after that, you send it to the cooler. Alright, the cooler is where the heat will be rejected. Can you see now? This is the last one, the last item here. Okay. So now, after cooling, it goes back to our original state. That means when the steam comes, when the gas comes out here, it will lose the pressure, it will lose some temperature also. Right? So now when you further cool it down, it will lose. The temperature will be caused to go even lower, then after that, we go back to the initial point. So it works in a cycle. Okay? Now that cycle is, you can see now, right, over here. Alright, this. Okay, okay, before. Alright, the cycle is here. Alright, this I think probably you have to take down because this one is the solution to the okay. So if you like, you can start taking down now so that at least right, you will not get out back later. Okay. So now one to one, I have now the TS diagram here, the PV diagram. So now it's very easy to follow. The cycle now is 1, 2, 3, and 4. So 1, 2, 3, and 4. So we turn back. So 1, 2, 3, and 4. So now if you go to the cycle, you know, during the compression is here. Alright, isentropic compression. Can you see now? Alright, very similar to what we have discussed in our all these cycles. 1 to 2, entropy is here, isentropic compression. Alright, so on the PV diagram, you follow 1 to 2, just like our line here. Okay? Right? Then after that, 2 to 3, what is it? 2 to 3, you added heat. Q1. So how is heat added? Heat will be added at constant pressure. Can you see now? Alright? But of course, 2 to 3, this is a TS diagram. This one is the sloping line because when you add it, the temperature will go up. But this one, you can see, is the constant pressure line. So heat will be added at constant pressure. Can you see now? Q1. This one here. Alright? Then after that, it expands from 3 to 4. So 3 to 4 is 3 to 4 expansion. And the expansion is here 3 to 4 isotropic, meaning to say reversible adiabatic. So reversible adiabatic. Okay? Then 4 to 1 cooling, and the cooling is done at constant pressure. PV diagram, this is the constant, right? Because the horizontal line, the cooling is at constant pressure. Alright, so now of course on the TA diagram, this one must be sloping because the temperature must be dropping. Correct? So now from 4 to 3, what happened is okay, 4 to 3 is our heat rejected Q2. Okay? Now so this is the process and so on. Now how do we evaluate this? How do we analyze this? Now this one is simple. The 4 items that you see here, you will evaluate. Okay? 1 to 2, reversible adiabatic compression. Can you see now your gamma? Alright, PV ratio of power gamma is a constant. So remember when we talk about this adiabatic process, there is a set of 3 equations. So now you want to know the origin of this equation, where they come from, you will have to go back to your what? Your book, right? Right now. So that's how you were here. Okay. Reversible adiabatic. Can you see now these 3 equations? Alright, so anything come from there. So now the thing is very simple for you. The equation is here. So meaning to say this formula allows you to find temperature and pressure. Okay? Alright, so this one is during the compression. Okay. Then next one, 2 to 3 is constant pressure heat addition. Now this is simple. Because it is constant pressure FCP T3 minus T2. T3 minus T2. Alright? Okay. And then now 3 to 4 is the expansion where work comes out. Alright, so during this expansion is reversible adiabatic, so this formula applied. So this process and this process, they are the same. Only thing, one is compression, one is expansion. So you notice the formulas are the same. Alright, but of course the state point are different now. You use the correct state point 3 and 4. Alright, and then finally 4 to 1 is cooling, heat rejected. So heat rejected is also at constant pressure. Alright, constant pressure. So now NCP T4 minus T1. So this process and this process, both heat transfer are the same process. Only thing, one is heat added, one is heat rejected. So it's important thing to know is that these are constant pressure process. How you know they are constant pressure process now? Because according to theory, my Joule-Brayton cycle is this. Alright, so can you see now constant pressure, constant pressure. Alright, so what are these constant pressure? Heat transfer. These two lines are work transfer. This one is compression, this one is expansion, this one is heat rejection, this one is heat addition. That's why now heat added is at constant pressure. Joule-Brayton cycle is easier. This one will be more complex. Okay, that's why I give you the work solution. Alright, you go back, maybe you can follow the calculation. That means to say now essentially the calculation involve formulas that are taken from what? From the table. Alright, the relevant one. Correct or not? Okay, like all these formulas come from there. Right? This will be the only one adiabatic involving gamma. The other one, of course, the heat transfer. Right? So that's the theory. Okay, so now what you're seeing now is the
heat transfer.
Work example, so I think I've given up the lecture. You turn over, you only have this question. Alright, so now to solve the question, here is the solution. Maybe you would like to keep it down. Alright. I suggest you take down at least some practice, alright, because we don't have tutorial and so on. Alright, so as you take down, more or less you can practice, alright. Okay. Alright. So you notice, you see how the formulas are being used. I mean, you try and understand the reason of the working. A stationary power plant operating on an ideal Brayton cycle at a pressure ratio of 8. Right. The gas temperature is 27 degrees at the compressor inlet and 1027 at the turbine inlet. Determine the gas temperature at the exit of the compressor and at the exit of the turbine. Determine also the thermal efficiency of the cycle. Okay? So please, these are the terms that you must know. I think thermal efficiency, I've gone through the definition of how it is. Network over what? Network got bigger and bigger. Network over now I think the question you don't need because the question is there. Now the thing that I want to draw your attention will be this, right? When you use formula like this, the temperature must always be Kelvin. You notice now all the temperature I converted to Kelvin for this. You don't ever use centigrade or Celsius inside the formula, right? In thermodynamic equation, always like that, right? The temperature must be absolute. So now this part you must know, right? Absolute temperature and your Celsius. Okay? So to summarize the step, the first thing you do is you find the temperature because your efficiency is given by net work done over heat transfer. Okay? And the net work done itself is given by Q2 minus Q3. Alright, Q1 minus Q2, sorry. Alright, I have here Q supplied over Q rejected. Alright. So the next thing is to find out the heat rejected and supply, and then these two formulas apply, MCP, G2. Very simple. Okay, as long as you know the step. Okay, and then for the property, one thing I think I have to show you is what? This MCP, this one, alright, because the system, the turbine cycle is using gas. Sorry, using air. And that is the property of air. So I think this question was given, so no problem. Alright, Cp, okay. Alright, so gamma is 1.4. So please always so-called memorize this. This is like property of water like that, right? So if the moment you see this is for air, gamma is 1.4. Cp was 1.005. So I think essentially when given the question, the property will be given. Okay? In the case of exam, right, if it's not given because they have open book exam, I go to the book and look out. Okay? Alright, so let me this one must be the property of the air, because the whole cycle uses air, so it's the property of air. The property of air. Okay? Alright, so with that, let me just go through the example on the dual combustion cycle here. Okay? Now you notice there are some things which we have not discussed earlier. So that means to understand the solution, you have to probably read the textbook on the dual combustion cycle. Now the reason why I give you this work example because it contains the application of the formula. Alright, correct? I mean we don't just learn the formula, right? But when we apply, how we apply. So some of these terms, alright, involving the cycles, okay, they are very specific. Like for example, your compression ratio, your cutoff ratio, right? So I think you have to read the notes, right, to get out all this information. What are the definitions? Alright, okay, to understand the problem. Otherwise, you won't understand the problem. Okay, what I got to here is only the theory, right? You can see, right, the theory is here, but when you work out, this is what it involves. But of course, to solve this one, you must have the backing of the theory. Alright, let me say, to solve your combustion cycle, you must understand the theory behind it. To understand this theory, we start off end up with your Carnot cycle. Okay, so that's why we all go to this. Right, now, so for this one, these are the compression ratio given, pressure, temperature, absolute pressure, kilonewton per meter square. Again, when you use formula, please make sure the units are consistent. Don't go and use bar for this. Right? Because, right, kilonewton per meter square. You see, 1 bar is 100 kilonewton, so don't use 65 bar, alright? Change it to kilonewton per meter square. So it must be consistent, temperature must be Kelvin, so on. Otherwise, the answer will become very, what is called, meaningless, alright? And it's just a lump of nonsense, I can say, because they are not consistent. Okay? So later on, you'll see now, all these formulas come from the process. Okay? So let's take a look, alright? 1 to 2, remember 1 to 2 follows your PV rate about gamma as a constant, reversible adiabatic. Alright? So governing the temperature are this formula, reversible adiabatic. So this formula can be found from the table. Know what you are looking for, and then from the table you get the formula. Alright, so this one you find T2. Okay? So same thing, like the value for gamma and so on. Later on you will have to find Cp, Cv, right? These are the values. Right? Because your gas power cycle will use air. Alright, it will use air. So air is our working substance inside. So these are the property of air. Alright. Try and remember this if possible. If not, find it from the book. The book, it will be scattered all throughout. You just pick it up from there, right? Either from the book example or from the actual table, right? All these formulas. Okay? So now the whole idea is to find the temperature. Okay? So next one, you have to find T2 in order to find the big one, right? That kind of thing, right? Okay, when you go through this, you will know the reason for finding it. So I need to know the temperature before I can find it. Okay, this one now, 2 to 3. 2 to 3 is constant volume. So this one will be governed by constant volume process. You go to constant volume process table, you will find the formula there. Alright, that is to say now it's time to apply what you learned, okay? Put the pieces together. Don't go and use this formula for this, That means to say you just don't understand what you are doing, alright? Correct or not? This formula is only applicable for this 1 to 2. 2 to 3 is constant volume. Correct or not? We have constant volume process, polyatomic process. So now this formula will be used. So this formula, you go to constant volume process table, you will find it there. Okay, the purpose now you find the mean temperature. Okay? Alright, and then after that, having done that, this one now to find T4. Alright, so T4 is very special now because you are given the amount of heat transfer, right? It's a fraction of the others, right? What did you say? Something like 60% or what, is it? Let's look at it. Look at the question, right? Slow combustion cycle. The heat added at constant volume is 60% of the heat added at constant pressure. So that's what it means, right? Heat added at constant volume is 60% of heat added at constant pressure. So heat added at constant pressure, alright, heat added at constant volume here. This is our theory. Alright, correct now. So now we can find C4. Okay. Now when it comes to here, compare with the cut-off ratio, it's tricky, so I think I will leave this for you to go back and read. Right. First, you have a definition of your cut-off ratio. Okay? Just like we have now compression ratio, because this one describes the engine. Right? The moment you have an engine like that, remember you have stroke, bore, alright, and then you have compression ratio, okay, and then you have cut-off ratio. Alright, so this one you go back, alright, pick up the definition. Your cut-off ratio is actually V4 over V3. Okay, volume V4 over V3. Your cut-off ratio is actually V1 over V2. Alright, these are definitions for the term. More or less you have to know the definition. Okay, so now below all these is a bit of trick. So again, I'll leave it to you to go and follow it at your own time. Okay? Alright, try and understand this part, right? Because if you can understand the so-called construction of the question or the construction of the solution. Right? So go through it. Alright, go through it. This one can be found If it is not clear, right, in your book also you carry, okay, alright. Okay, so the heat supply is our Q1. Can you see now it is here, down here. Correct now? Alright, so you can apply because by then all the temperature will be known. You can work out Cp, Cv for air. Right? Property, get it from the table, from the book or whatever, or maybe you can memorize it. Hopefully when the question is asked, it is given. Okay, so now I have heat supply, heat rejected. Where is my heat rejected? Q2 mCv T5 minus T1. That's T5 minus T1. Okay, in this formula now, right? So heat rejected is here. Alright, so work done is the difference of heat supply and heat rejected. So free efficiency is here. Okay. We have an overall theory, but when it comes to nuts and bolts, how to solve it, we require formula. That formula requires to come from your table. Your quantum volume process. Right. Why do we have quantum volume process here? Right. Sometimes you may have to use quantum process. Right? For example, right? We have quantum volume process here. We have quantum volume. This is heat added. Okay, we have quantum volume, right? And then we have this one quantum pressure. Okay. So that's how all the parts will come together now. Okay. What we actually have done, right, is that when we went through the theory, we moved very quickly. So we wrap it up by using an example like that, when the formulas, relevant formula are used, right, to incorporate into a question that way. Alright. So of course we are not able to do all the questions now, right? In your textbook you notice there are so many examples, right? We don't have the time to do that. Okay. Alright. So but for you notice that for your combustion cycle, it is a combination of these two, right? That's why the name dual is there. Correct now? That's why the name dual. Two. It's made out of this and this. Right? You notice now, right, all the other sides are the same except for this part in it. Correct now? This one is constant volume is added, this is constant pressure is added. When it comes to here, it's made up of two. The rest of the processes, they are the same, identical, no change. Can you see now? That's why we can easily, kill 3 birds with 1 stone, because essentially they are made up of the same processes. Okay? Alright? So I think we are fortunate, we can make it. Alright? So any question now? Tell me, Mr. Sivaras has a review on the question or reading thing. I think it should be okay already. Huh? So okay, I think we will get end here now.